Hi, this paper describes a new framework for statically verifying ReLU neural networks, that is, these particular feed-forward neural nets made up of linear layers followed by ReLU functions. This static analysis will allow us to give over approximations of ranges, and will show how this permits to show some specifications correct. So we're going to use tropical polyhedra, an abstract domain, which is designed for dealing with the main difficulty of abstract interpretation of neural networks. That is, that these are inherently nonlinear. And so using classical convex abstract domains is going to be too imprecise. Or if you use disjunctive analysis, it's going to take too much time to analyze. So if you really think about what these neural nets are computing, of course, it's reasonable to change point of views and use tropical arithmetics, because they are particular rational functions when you use tropical arithmetic, so that you can further abstract these rational functions by linear tropical functions or polynomial rational functions in a neat way. Tropical arithmetics is based on the so-called tropical summiring, where you replace the classical addition by the maximum operation and the classical multiplication by the addition. So it's almost like computation with real numbers as you're used to, except it's a summiring. You don't have inverses for addition, but still you can define geometric objects as you are used to, like tropical half spaces. Tropical half spaces are given by affine inequalities of that form. Sum of AI xi plus c is less or equal than sum of bi xi plus d, where ai, c, bi, and d are real numbers. If you look at the plane, then these half spaces are of one of these shapes, and they're symmetrical in pink and in blue. And of course, if you think about the ReLU function itself, its graph on -1, 1, which is this blue broken line, it is just a tropical segment. So it will be a particular tropical polyhedron, which is an intersection of tropical half spaces. All convex combinations, classical convex combinations, are going to be very coarse on the ReLU function. If you use polyhedra, you get a gray triangle here. If you use zones, it's going to be that particular parallel top in gray there. I'm not going to go into much detail about the way we can represent these tropical polyhedra. It's as with the classical polyhedra. We have a double description method. We have an external view, an external representation of tropical polyhedra with constraints. So these conjunction of tropical linear inequalities as written here, and also an internal representation as a convex combination of extreme points and generators. It's fully described in a former paper of ours in Stacks 2010. What you have to understand for the rest of the talk is that max plus polyhedra are particular disjunctions of zones. Zones which have been used extensively in program analysis and in model checking. So it's just polytopes with faces 0 or 45 degrees with respect to the Cartesian axis. And of course, there are close relationships between these tropical polyhedra to zones. You can always also over approximate in the best way tropical polyhedron as a zone. It's given by this computation of a residuated matrix, which has been spelled out, for instance, in our SAS 2008 paper. So from this ReLU graph, which is a tropical polyhedron in blue, you're going to get this gray zone exactly. But also in this paper, we show that any closed representation of a zone is actually an external representation of a tropical polyhedron, and can be made an internal representation. You can find these n+1 extreme points A and BK, whose tropical convex combination is going to give you the corresponding zone. So the zone is in gray is the convex combination of points A, B1, and B2. It's done by a simple computation on this constant Cij, as you can see here. So, of course, we had this tropical abstract domain, which we used for program analysis for dealing with arrays, basically. So we have a join and meet operations. You can see a join of two tropical polyhedra here, but we have to design a specific abstraction for classical linear assignments for dealing with these linear layers, which are actually non-tropically linear in our tropical framework. And we are going to do this by first using a zone abstraction of a linear function f from Rm to Rn. So it's proposition 3 of the paper, and then use what we just saw, the representations, the internal and external representations of zones using tropical polyhedra. And we see that we can always represent in some sort of optimal manner in some ways externally this graph of function f by this tropical polyhedron given by m plus n plus 1 affine tropical inequalities. And we can also represent it internally as a convex hull of m plus n plus n plus 1 extreme points. All these constants, capital M, small m, delta, c, and d, are actually given in closed form from the constants defining f. So it's easy to describe on simple examples. For instance, for f from R to R, you have three cases. If the slope of f lambda is negative, if it's decreasing, then the best abstraction is actually a box, an interval-based abstraction. If you have a slope which is positive, then you have two cases, above 1 and below 1, gives pretty similar shapes, actually, the green shapes here. And you can see that in all three cases, this is internally described as the convex hull of 3 points. So m plus n plus 1, 1 plus 1 plus 1 points. For f from R2 to R, the representation will depend on the signs of lambda 1 and lambda 2 and the respective positions with respect to 1 as well. And you can see their abstractions in three cases. The graph of function f is given by the darker green plane, and the lighter green region is the tropical polyhedron, which is produced directly from function f. So just to give you an idea of what the static analysis will do on a very simple network, let's take this network with two inputs. The weights are indicated here. The biases are B1 and B2, which are respectively -1 and 1. And this is here the linear layer giving H1 and H2. And then the output layer gives the outputs Y1 and Y2 by these max formulas here. And we're going to use our tropical abstraction to prove two properties, not only the ranges, but also two properties, P1 and P2. First property tells you that we're always going to classify class 2, the one given by neuron Y2. So it's equivalent to saying that we're going to prove that Y2 is always greater than Y1 for all inputs. And P2 is going to be a robustness property. That is, whatever the input X2 is going to be within -1 and 1, if X1 is small enough, then the output Y1 will never be very big, so will never be above 0.5. So if you look at the exact ranges, P1 and P2 are going to be correct. So you see in the H2, H1 plane, you're just going to rotate by 45 degrees the input square, X1, X2. And when you take the ReLU function, you're going to get in the plane Y2, Y1, the blue triangle here. So you see it's above the diagonal, so Y2 is always greater than Y1, so P1 is correct. When you look at the H1, X1 plane, you see that parallel top, and taking the ReLU function on this parallel top gives you this funny shape, which is actually a tropical polyhedron, blue segment and this blue triangle. And you can see that the specification P2 tells you that the output Y1 in blue should not intersect the red region here, which is the case. So P2 is always going to be true. Of course, we are interested in knowing whether our abstractions are going to prove these two specifications correct. And this is indeed the case. With the zone or with the tropical polyhedron abstraction, we're going to get for Y2 as a function of one, something a bit more than twice as big as what we would normally get exactly. So twice as big as this triangle. So it's going to be that tropical polyhedron here. But we're going to get the exact computation of y1 as a function of x1. As I told you, this segment plus triangle is a tropical polyhedron. We can refine actually this abstraction here to get smaller abstractions closer to the triangle here by subdividing the inputs and then taking the unions. Unions are computed as tropical polyhedra, and if you further subdivide, you get something closer and closer to the blue triangle, which is the exact result. So it's actually quite fast because these 4 subdivision gives you a tropical polyhedron in blue, which is the convex hull of just 4 extreme points. In the paper, we're also describing the multi-layer abstraction. So if you add up a new layer, what we're going to do is to first abstract the first layer, then take an hypercube envelope outer approximation of the output, which loses information, of course, but which is the basis for the interpretation of the second layer using tropical polyhedra. And we recover some of the dependencies we lost in the process of abstracting the first layer by an hypercube by intersecting the tropical polyhedron representing the input-output relations of the first layer with the tropical polyhedron representing the input-output relation for the second layer. So this is fully exemplified in the paper. In that case, we're recovering some of the dependencies between the inputs and the outputs of the full neural network. Also in the paper, we describe how the range analysis is able to prove such specifications as P1 and P2. So of course, if specifications are given by these affine functions, there are 2 methods we can use. One is to take the zone abstraction of the tropical polyhedron that our analysis gives, and then use a linear programming problem to decide whether this linear specification is positive or not. This is enough for checking P1, but not P2, as we saw that any convexification of the output would actually contain some bits and pieces of the red zone. But the method 2 will be more expensive and will be able to prove P2. The second method is to actually use a non-convex optimization problem encoded as a mixed integer linear programming and solve it with specific tools like Gurobi, for instance. Finally, in the paper, we discuss the curse of dimensionality problems. Of course, with the double description method, we're going to blow up as with the classical convex polyhedra with more than 100 or 500 neurons. It's going to cost a lot of time, whereas any of the internal, as here, or external representations we can propagate is going to be quite fast. So of course, there are discussions in the paper about what internal and external representations are good for. Internal representations are better for unions or better for dealing with subdivided inputs, for instance. And of course, there's more in the paper about all these things. So in the future work, we have, of course, many things. I mean, this paper really opened new venues because we've been just considering linear approximations of these tropical rational functions, but we can go to tropical polynomials quite easily as a first step. So thanks a lot for your attention, and let me answer any questions.